In this video, we shall look at how to perform differentiation of implicit functions. When two variables are connected by an equation which doesn't express either of them explicitly in terms of the other, each is said to be an implicit function of the other. The general equation connecting, say, variables x and y implicitly may be denoted in the following manner. fxy equals to 0, but this is the implicit function. We can sometimes solve such an equation so as to express one of the variables in terms of the other, say y in terms purely of x. But this is not always possible, and it is not necessary for the purpose of differentiation. For example, let the equation be the following. Let's try to calculate dy dx. How do we do it? Let's take the derivative of all the terms in this equation one by one with respect to x. When you take the derivative of x squared with respect to x, that will give you 2x. The second term, how do you take the derivative of y squared with respect to x? To do that, we sort of use taking the derivative of a function method, like that. And that, it's going to be 2y, and the dy dx will just follow. Now the term on the other side, this is just a constant, so the derivative is quite simply 0. So solving for dy dx, we immediately get minus x over y. Let's look at the following function. Differentiating term by term, the first one will give you 2x when we differentiate that with respect to x. The second term, remember, we want to differentiate this entire thing with respect to x. So let's apply the product rule. 3 is just a constant, you can take that out. Differentiate the first one, which is simply x, so if you differentiate x with respect to x, you get 1. You multiply that with the second term, which is y, plus you write the first term and then you differentiate the second term with respect to x, and that is just dy dx. Now let's do the third term, which is y squared. From previous example, we know it is quite simply 2y dy dx. And 3 will simply give you 0 when you take the derivative of it. Rewriting the above result, you get 2x minus 3y minus 3x dy dx plus 2y dy dx equals to 0. Factoring out the dy dx terms, you get dy dx bracket 2y, that is this term, minus 3x, that is that term, and move all the other terms to the right, you get 3y minus 2x. That means dy dx is 3y minus 2x over 2y minus 3x. And that is the answer. How do we determine dy dx for that function? Let's do one by one. Let's look at term number 1. Taking the derivative of 3x cubed is pretty simple. It's just 9x squared. Now the second term. Plus 2 is just a constant. Let's apply product rule. Differentiate x, you get 1, and the y squared follow, plus write the x and differentiate y squared with respect to x, and that will be 2y dy dx. The other side, differentiating 2y, is again just 2 dy dx. And differentiating 3 with respect to x is just 0 because 3 is a constant. Let's rewrite the above equation. 9x squared plus 2y squared plus 4xy dy dx equals 2 dy dx. Now we can solve for dy dx. And when you solve for dy dx, you get 9x squared plus 2y squared over 2 minus 4xy. And that's the answer. Let's find dy dx for this function. Before we do anything else, first we need to use the trigonometry identity to expand the right-hand side, which is sine 2x cosine 3y plus cosine 2x sine 3y. So let's differentiate term by term. The first term is just dy dx. Now the right hand side, we have to use the product rule. First we differentiate the sine 2x. That's going to give you 2 cosine 2x. Multiply that with cosine 3y plus, now differentiate this with respect to x. That's going to give you 3 minus sine 3y dy dx, and multiply that with sine 2x. How did you get this term when you differentiate that with respect to x? We have d dx cosine 3y is d dy cosine 3y times dy dx. So that's how you get this term. And sine 2x just follows. Now let's do this. So again, you differentiate this with respect to x. That's going to give you minus 2 sine 2x, because when you differentiate cosine, you get minus sine. Sine 3y follows. And now you differentiate sine 3y with respect to x, just like you differentiated cosine 3y with respect to x. And that's going to give you 3 cosine 3y dy dx. And you write cosine 2x. Just multiply that. Again, using trigonometry identity, you can combine this and this as 2 cosine 2x plus 3y. Likewise, you can combine this term and that term using trigonometry identity in the following manner. Plus 3 dy dx cosine 2x plus 3y. The left-hand side is, of course, dy dx, namely this. Now we can solve for the dy dx. So it is just 2 cosine 2x plus 3y over 1 minus 3 cosine 2x plus 3y. And that's your answer. Let's find dy dx for this following function. Now note that a is a constant. So we do one by one. Differentiating y with respect to x is just dy dx equals a is a constant, so that is just 0. Now this term, we can use product rule. First differentiate x, you get 1, and then simply write the second term, plus write the first term and differentiate the second term, namely exponent y, with respect to x. So that is just d dy ey dy dx. So the first term will become e to the power y plus x. Now what is this? That is just e to the power y. When you differentiate exponent y with respect to y, you get back the original function. And don't forget dy dx. Now let's write down dy dx, which is just e to the power y over 1 minus x e to the power y. And that is the dy dx that we seek. What about this expression? How do you find dy dx for it? One way to proceed, because it has this powers, is to take the natural logarithm of both sides. So the left hand side is natural log 3x plus 2y to the power 3 equals natural log of 4 plus natural log of 2x plus y to the power 4. Note that this 3 can be brought forward in front, and that gives you 3 natural log 3x plus 2y equals natural log of 4 plus, you do the same to the power 4, so 4 natural log 2x plus y. Now let's start to differentiate with respect to x. So 3 stays. You want to differentiate this function with respect to x, like that. And the right hand side, this goes to 0 because it's a constant. You have 4d dx natural log of 2x plus y. Let's use the function of the function method. So the left hand side would read d over d 3x plus 2y natural log of 3x plus 2y d 3x plus 2y over dx. And likewise, for the right hand side, it would be 4d natural log of 2x plus y over d 2x plus y d 2x plus y dx. Let's do the left hand side. The left hand side is just that 3, and this is just over 3x plus 2y. It's like you're differentiating natural log of x with respect to x, and you get 1 over x. Now this term. The first term will simply give you 3. The second term will give you 2 dy dx. Let's do the right hand side. 4. This will give you over 2x plus y. Now that one, differentiating 2x with respect to x is 2. Differentiating y with respect to x is dy dx. From this point onwards, it's just algebra. Let's bring the dy dx terms to one side. You're going to get 6 over 3x plus 2y dy dx, that's that term, minus 4 over 2x plus y dy dx, that's that term, equals 8 over 2x plus y, that is this term, minus 9 over 3x plus 2y, that is this term. Making the denominator equal on both sides, you end up with that result, and you see they're going to cancel. This left hand side is just minus 2y, because that terms would cancel, and 6y minus 8y is just minus 2y. Likewise, on the right hand side, it is just 6x plus 7y. And thus you arrive at the desired result for the dy dx, which is just 6x plus 7y over minus 2y. And that is the answer, which solves the problem. Thank you for watching.